Okay, so in this video, we're going to talk about integration by parts. I'm going to just break the whole thing down. So integration by parts is really, it's a formula. So it's a formula as you see here. So I want you to notice just the original format of this. Integration by parts is a way to integrate things that look like this. U of x times v prime of x dx. This looks very general, and it is very general. So the idea behind this is that you can force things to work like this. And if you force them in the right way, then you can integrate them by this formula. U of x times v of x minus the integral of v of x times u prime of x dx. So this is, I'm going to show you like different ways of how to set this up, because this is not always going to be obvious of how to actually set this up. And then once you figure out the right combo, then there are some steps that kind of show you, oh, okay, I've set this up in the right way and now I can integrate. So this is a way to integrate things that we probably couldn't previously integrate. Now, the shorter format of this formula is u dv equals uv minus v du. This is what people remember. So this is the integral of u dv equals uv minus the integral of v du. But I feel like a lot of people, when they go through calculus, they remember u dv equals uv minus v du. I can still recite that in my sleep many years after taking calculus. Okay, so the easiest way to learn this, honestly, is if we just jump into some examples. So I've got the integral of x cosine pi x dx. So first of all, just appreciate, right, I cannot integrate this with just a standard integration formula, okay? So this obviously needs some sort of trick. I cannot just use, say, like substitution, so that also wouldn't work. So I'm kind of out of options here, and so this is where integration by parts comes in. So the first thing I want to do is I just want to show you all your different options of how to think of this. So I've got this integral, right? I need to view it in this form, u of x times v prime of x dx. Okay, so I need to choose something to be my u and something to be my v prime. Now I'm going to call v prime dv, okay? So I've outlined 4 different ways to do this, and I really want you to appreciate this, okay? So in option A, I say this is my u, this is my dv, okay? In option B, I say this is my u, and the x dx is my dv. Another way I could do this, I could say that my u is this entire thing here, and my dv is just 1 dx, and then I do the opposite for d. So my u could just be 1, and then my dv is going to be x cosine pi x. Okay, so I'm telling you this because I want you just to understand that there is some creativity involved in this, in how you set your u and v prime. And you have to kind of think critically as to what of these options make the most sense. Now, there's one option that immediately does not make sense, because if I think about this dv, so one of the goals, so if we just go back to the formula for a second, so I just want you to appreciate what we have to do. So I set this v prime, and notice that I have to eventually get v. So what this means is that I'm going to have to integrate whatever my v prime is. And then also notice for u, I have to take the derivative of u. That's kind of like baked into the formula. So going back to this, one of these options definitely does not make any sense. It's this option here, because if I have to integrate this x cosine pi x dx, that's literally what my integral is, right? So this option makes no sense because I already don't know how to integrate this. So you can kind of figure out some intuition on this, like as far as what's probably not going to work, if you just think about, you know, it from that standpoint of like some things you just can't integrate, so that's not going to be the option. Now, if I look, the other options, all of these other options I can integrate. So now I need to think about what my u is. And so the best choice of your u, this isn't always going to work, but there is an ideal scenario. Your ideal scenario would be a u that ideally, when you take the derivative of it, the derivative could eventually turn into a constant. So if I take the derivative of cosine or x cosine pi x, both of these, I can take a million derivatives of these two and never stop taking derivatives. So if I look at u equals x, if I take the derivative of this is just 1. And that's the other big sign then, that these two are not what I want. This is the option that I want to use. So when this lines up, this is your ideal scenario, and so this is what you would like to move forward with. So here is my x is my u, and then my dv is going to be this cosine pi x dx. Okay, so to finish this now, and I've set this up, as you can see here, so now I have to figure out these other pieces. So I have to take the derivative of u, and then I have to integrate to find my v. So let's do that. So if I take the derivative of x, that's 1 dx. And then if I integrate this guy here, so this is going to be 1 over pi sine pi x. I don't need the plus c just because of we're setting this up, so you don't need the plus c. Okay, so here's all my pieces, and from here I can just remember my formula now. So remember, it's u dv equals uv minus the integral of v du. I would also like to take a moment to mention here, if your handwriting is sloppy, that's really going to work against you. So you will find as you move through a lot of science and math classes that having good handwriting is going to be very important. I started making my u's like this. I used to make them like this, but then I would get confused with when I would make like a softer v. Let's see if I could make, I can't even make a softer v anymore. Maybe something like this. So I used to have much messier handwriting, and now I'm a little bit more intentional. So my u's always have a tail, and my v's I put a really clear point in. So I know that's like a tiny thing, but this is always a complaint I kind of hear about this particular technique. Okay, so I chose my u and my dv, so now it's just a matter of just plugging this stuff in, okay? So I have my u and my v, so that's going to become 1 over pi x times sine pi x minus my v du. So that's going to be this and this. So that will be 1 over pi sine pi x, and then times 1 dx is just going to give me dx. Okay, so now appreciate what I've done here. This I could not integrate. I've used this formula, and this integral I can integrate. So this is what we're looking for, is to rewrite this in some way so that I end up with an integral that I actually can work with. That's our ideal scenario. So then I can finish this. Let's see, so the derivative of sine is going to be negative cosine, so the sign here flips. And then, let's see, this will be cosine pi x plus c. Okay, so there is my integral, okay? So this is like the nicest, easiest case of integration by parts, and you'll see why. So the best thing about this was that my u was immediately turned into this constant 1 dx. You will appreciate as we go through a few more examples why this makes this the easiest one. Okay, so let's keep going. Let's move on to another one. So now we're going to integrate the natural log of x dx. Now, perhaps once upon a time, you thought that this is an integral we could not do, but my friends, we are now going to use the power of integration by parts to do this. Okay, so once again, I'm going to set up my little template here. Okay, so I need to select a u and a dv to do this. Now, in this problem, there's actually not a lot of choices here, because I've really just got this one function and then this dx. So this natural log, I wouldn't choose it as my dv. So remember, maybe I'll just highlight this and this. These are the two things that you have to pick, okay? And so this natural log is obviously not going to be my dv because I don't know how to integrate it. So like I'm just kind of forced into my natural log has to be my u, and then my dv has to be my dx. So in this case, it's just a matter of what I can actually integrate or not integrate. So I'm left with this. Now, I know we haven't talked a ton about this, but I actually think you know enough now to try to finish this one on your own. So what I want to suggest is that you now take the derivative, integrate, and finish this, and just try to plug the whole thing in, because I think you actually know enough that you can finish this on your own and get a little confidence with this technique. So pause here, give it a try, and then hit play when you're ready. All right, so I'm going to integrate natural log of x, and then if I take if I integrate dx, this is going to become x dx, right? Because it's just 1, so if I integrate 1, that'll be x. Okay, so now I just plug everything into my formula. So this will be uv, so that's x. Oops, sorry, I wrote a dx here. That wasn't supposed to be there, my bad. Okay, this is going to be x natural log of x minus, so then my v du. So that'll be x times 1 over x dx, right? Here's my v, here's my du, here's my uv, so there's everything. And this I can integrate, right? So again, this tells me, okay, I've definitely done the right thing here. So I'm just going to integrate 1 dx. So my final answer is x times the natural log of x minus x plus c. Okay, and so this is another one of those nice cases where, like, in some ways, I almost think this one's like easier than the last one, because you don't have a lot of options as to what your u and your dv are. So if you understand kind of like the nature of how to pick these, this is like also a nicer, easier, if integration, if we could call integration easy, this would be like an easier example. So okay, now let's turn up the volume a little bit, my friends. All right, so next I'm going to look at this example. And we have some knowledge now of like how to approach this. So I need to choose my u and I need to choose my dv here. Now, I'm just going to go ahead and tell you the plot twist to this problem. The thing is that with integration by parts, it's 100% possible that you would have to integrate more than once. So when I look at this, I have two options. This feels very similar to where we started, but the thing I want to do here is I want to choose whatever part of this I know that I could eventually integrate to get a constant. So I have x to the third and e to the x. So which one of these two could I, oh, I think I said integrate. This is like flips in my brain. Okay, it's whichever one of these you could take the derivative of enough times to eventually get a constant. Okay, so which one of these is that? It's going to be x to the third, right? So if I take enough derivatives of x to the third, I know that this eventually will turn into a constant. So this will be my u, and e to the x will be my dv. So then my du will be 3x squared, and my v will just be e to the x. Oops, and I forgot my dx. Okay, now here's the deal. If I set up my uv, so let's see, I'll just go ahead and set up my uv. So this is x cubed e to the x minus my v du. So that'll be 3x squared e to the x dx. So this is my v times my du all multiplied together. Okay, so here's the deal. I still can't integrate this, right? But I'm making progress, because now instead of having x cubed, I have x squared. So I'm making progress on this, and now I have to start the process over. So now maybe what I'll do it in a green color so that you can notice that we're starting this over. So now my u, actually let's make our lives just a little bit easier. Let's bring this 3 out so that I don't have to worry about it, okay? Okay, so now my u, I've got my u and I've got my dv. So I'm going to start the process over. So my u will now be x squared. X squared. And my dv will still be e to the x dx. Okay, so now if I take the derivative of x squared, this is 2x dx, and my v will be e to the x. Okay, so see how this is making progress, right? So I'm getting smaller and smaller powers of x here. This is a very normal thing to have to do with integration by parts, to have to integrate multiple times. Okay, so let's make a little space here. Okay, and so now we're going to keep going. So I still have the first part of my integral, right, minus 3. And now I have to start a new integration by parts for this part here. So I'll do this part in green just so you can track me. So I've got my u times my v, uv, so that's going to be oops, let me get this, x squared e to the x minus my v du. So now my v du is this e to the x and 2x dx. So this is going to become 2x e to the x dx. Okay, and so once again I'm making progress. now this is a smaller power, so I can integrate again using integration by parts. Once again, I'm going to just take the constant out. Actually, I'll leave the constant in this time. Why not? Okay, so I need to now use integration by parts on this part. So my u and my dv, I have to select those. So my u will be 2x, and my du will now be just 2 dx. My dv will still just be e to the x, so that my v is e to the x. Okay, so we'll make space again. And so now, still got this x cubed e to the x minus 3, and then we had this version of integration by parts, and now I've got this new version of integration by parts, so I'm going to put up another set of parentheses. So now I've got to do it again. u v 2x e to the x minus v du. So this would be minus 2 e to the x dx. Okay. Whew. All right, and now we're good. Okay, so now this is an integral that I actually can integrate, right? At this point, I still couldn't integrate because I had this x here, but now I have an integration formula for just e to the x. So now I can finally finish this. So let me keep my color coding going just so you can kind of follow everything. Let's see, this is still my x squared e to the x minus, let's see, 2x e to the x minus 2e to the x plus c. Actually, I'm going to leave the plus c off. We'll just add it at the end. Okay, so now I have integrated, and now I can just distribute and get all my signs right here. So just in the interest of time, I'll just show you now what it looks like after I distribute all the signs. Okay, so here's everything after I've distributed all of my signs. So you can pause the video and just double check. If your signs are not right, I would say just start from the outside in, write a couple of steps just to make sure you get all the signs right. Okay, and so this is an example, right, where you use integration by parts over and over, and you have like some sort of power that you just kind of keep decreasing in each step. So it's totally possible that you would have to integrate multiple times. Okay, so let's move on to the last one. E to the x sine x dx. So if you're kind of understanding now this idea with your u and your dv, you should notice an immediate problem with this one. There's no choice of u that is going to, that I can continue to take the derivative of, where I'll eventually get a constant, right? E to the x, this is just e to the x if I take the derivative 1,000 times, and sine x, if I take the derivative 1,000 times, I'm just going to keep cycling through different, the sine and cosine, right? So immediately just looking at this and thinking about this, I know that this is going to act a little different. So, okay, for this one, there's not necessarily a best choice of u and dv. So I'm just going to say u is e to the x. My du then will be e to the x dx. My dv will be sine x dx. And my v now will be negative cosine x. Okay. So let's just get this party started. This is going somewhere. So here's what I'm going to do. This might seem a little odd, but I'm going to rewrite the integral, and then I'm just going to write what this equals. So I've got my uv, so my uv is negative e to the x cosine x minus v du. So with my minus v du, there's a negative here, so a negative and a negative will turn this into a plus v du in this case. So this becomes e to the x cosine x dx. And so right now we're like, oh, bummer, I've still got same thing. Okay, no problem. We've got to just keep going right now. So let's make some space. And so let's start the process over. So now what I want to do is I want to integrate by parts on this part right here. So let's see, I'll do it in green just so that you don't forget. So I've got my u is still going to be my e to the x, so my du is still e to the x dx. My dv in this time will be cosine of x dx, so my v will be sine of x. Okay, so I want you to watch what I do here. I'm going to restate my integral. This is where we started. And I've got negative e to the x cosine x plus, and now I'm going to start the new integration by parts. So I've got my uv, e to the x sine x minus my v to u, which is going to be e to the x sine x dx. Okay, and so now I'm going to show you why did I continue to rewrite the integral. So there's actually a very important reason for this. Okay, so first of all, I don't even need the brackets, so I'm just going to get rid of those because I'm just adding everything, so no sign changes I have to worry about. Okay, so the thing I notice here now is that my integral has cycled. Look at that. That's the integral. This is the integral that we started with, and now I've cycled around to this integral. So I'm back to the place where I started. So I've always felt like this next part is kind of magic. But since the integral has cycled with itself, what we can do now is we can just combine these terms. These are now technically like terms, and this is an equation that I'm really trying to solve for. So let me make some space. Okay, so here's what I'm going to do. I'm going to add this integral to both sides. And now in doing that, I have two of these integrals. So this is now 2 times e to the x sine x dx equals, and I'll just write this so that the positive term comes first. I just think it looks nicer. Okay, so now, well, remember what I was trying to do, right? I'm trying to solve this integral, and now with the way that I've set this up, I can actually solve for this, right? I could just divide by 2, divide both sides by 2, and now I have an actual solution for this. So this is now a thing that you have to watch out for when you integrate. You have to watch for when the integral cycles, as this one did, and then you can finish solving for it as we did here. So when you notice that it cycles, one of the key steps is that you have to restate the original integral so that you can set it up as an equation to solve for. Okay, so I have more examples of all of these in some of my example videos. So if there's any that you want to check out more examples of, please check out my example videos. So if you found this helpful, please consider hitting the like button or subscribing to the channel, and I will talk to you guys in another video. Thanks for watching.